Hi, my name is Diane Gratz, and I'm the Biotransformation Group Leader in the DMPK department at QPS. And I'm here today to talk about human metabolite profiling, specifically metabolite profiling that comes from the studies for regulatory submission, which are also called HAME, which stands for Administration, Metabolism, and Excretion. So the key learning objectives for this particular presentation are metabolite profiling and the importance of the clearance mechanisms and the systemic exposure of the drug-related material, how samples are handled and analyzed, and the reported data. So the kinds of data that you will get in these reports are the components as in the excreta as percent of dose administered, the percent of drug-related material that is circulating, the proposed structures for the metabolites, and a metabolic scheme. The objective of one of these studies is to understand the full clearance mechanisms of the drug and its metabolites. Typically, we do a single dose at the intended route of administration. So if your compound is going to be orally dosed in people, it's an oral dose for the radio-labeled compound as well. We also do generally a carbon-14 radio label. It has an advantage over tritium. Tritium can be unstable. You can lose it with water loss. And the position of the radio label is also important. If your compound is cleaved metabolically, you want to know that ahead of time to decide where the radio label should be. What we do in these studies is we measure the concentrations of parent and metabolites and determine the amount of radioactivity in the various matrices. And what we get from that is the primary mechanisms of elimination and excretion from the body. And the route of excretion may impact the need for DDI studies or special group inclusion. Drug-drug interaction studies can be necessary if, say, you have a compound that's renally cleared almost completely, and then you may need to worry about renally impaired people. Circulating metabolites, also known as systemic exposure, and the percent of drug-related material. What you want to do with that information is you want to compare it to the preclinical metabolite ID studies and see if the preclinical species have coverage of those particular pathways and metabolites. So right now I'm going to talk about the profiling timeline. These studies are long and very complicated. So just to go through it quickly, once we get the Q8 mass balance data, which is the radioactivity that's been excreted and the radioactivity in the plasma, then we create an analysis scheme. And then we pool the samples. We do radioactivity recovery for each matrix. That takes a couple of weeks. We also, as we're going, we also look at sample stability, and we do method development with an LCMS and with radio detector. Then we do metabolite profiling. That's really that's the long part of the study. Then we do radio-quantitation. After the profiling is complete, we do the radio-quantitation, and then we write the report. And the reports are long and complicated, so those take a couple of weeks. So it's really safe to assume a minimum of 4 months from the time that we get the mass balance data before your draft report is ready. For the study setup, we do mass balance. We get the mass balance obtained from the clinical site, and we look at the recovery of the radioactivity in the various matrices and decide how to do the pooling. The pooling schemes are based on the amount of radioactivity in the different matrices. For the profiling samples, you get one sample per matrix, and the sample is pooled across subjects and time points. For the radio-quantitation samples, those are pooled across subjects at each time point. And for the radio-quantitation, you'll have the radioactivity determines the number of samples analyzed. So if your collection goes out to 192 hours, but you only have radioactivity out to, say, 48 hours, we are not going to look at the later time points. The radio-quantitation that we also do for plasma is called an AUC pooled plasma sample. And AUC pooling, if you don't know about this, AUC pooling gives a single sample with concentrations of parent and metabolites that represent the total area under the curve of the concentration time profile. So basically what you get is as an early read to see is there inter-subject variability. Now, this is a small study, so you may not see it, but you may. So it has the potential to highlight unexpected phenotypic differences, such as things like cytochrome P450-2D6 is a well-known variable and in populations, and so you may have a normal range, you may have people who have are poor metabolizers, and you also may have ultra rapid metabolizers, and that may or may not show up in your study. So now I'd like to talk about sample receipt and profiling of the samples. The study samples are received on dry ice. They're stored at -70 until analysis. And one of the things that we look at as we're going is sample stability. What we look for sample stability is processing time, freeze thaw, and overnight in the auto sampler. Those are all things that we will look at and you will see reported in your draft reports. What we're looking for at that point is the stability of the radio profile. We're not just looking for the stability of the parent, because some metabolites are not stable and we would like to know that ahead of time. The profiling samples are pooled across subjects and across all the time points. So what you get is one representative sample per matrix, each containing greater than 85% of the radioactivity. And urine and fecal samples are pooled in proportion to the sample volume or weight. Plasma samples are pooled using equal volume aliquots. The profiling samples are really the bulk of the work for these kinds of studies. They're used for radioactivity recovery assessments, LCMS method development, and they're definitely used for the profiling and structural elucidation. And we start with the urine. Generally, that's the easiest one to start with. Then we go to feces and plasma as last. And the reason we do plasma last is because it has limited volume, and we're also likely to know all the metabolites that are going to show up in the plasma. The plasma is profiled in human studies. The plasma is profiled on the top count, which means we fraction collect and we dry down those samples, and then we do a static radio detection. This is because the radioactivity in human plasma is very low. Urine and feces may need top count. It may not. We may be able to do that with a radio flow detector. The radio-quantitation samples are pooled across subjects at each time point, and the number of samples is based on the levels of radioactivity in each matrix and time point. And the pooling scheme, you will get when we do the analytical protocol, you will see the pooling scheme that is going to be used for your samples. The radio-quantitation is performed after the profiling and structural elucidation, and it's generally one of the last steps in this study. The AUC pooled plasma samples are prepared and reported at this point also. They're also done after the profiling work. Now I'd like to talk about the recovery of the radioactivity and the sample stability. The recovery of the radioactivity, there's a workflow to your right, and that basically shows how we do things. And what we want to do is make sure that the metabolic profile is representative of the actual samples. So we're looking for as much radioactivity as we can get in each sample. For urine, basically what we usually do is we just centrifuge them. If they need to be concentrated, we can do that, but we also will need to reconstitute them, and we need to make sure that the reconstitution recovery is 90% or greater. The plasma and feces samples are extracted with organic solvents, and for those extractions, we need to get 85% or better of the radioactivity back. If we don't get that the first time with the first extraction, we will do another extraction. If we don't get it then, we may actually need to change the method and try different organic solvents, because we really need to get 85% or better. Once we have 85% or better, then we can go to the concentration and reconstitution step, and for that we need greater than 90% recovery. If we can't get 85% recovery in the extraction, we will talk to the sponsor, and this will be discussed so that we know we have a consensus on what the next steps should be. And the consideration for this type of thing is that if you can't get all the radioactivity back, your extracted samples may not represent your complete metabolic profile. And then how do you want us to calculate the amount of drug-related material for each component? And if the radioactivity is, if you can't get the 85% or better in the plasma, do you maybe have a covalent binding to protein concern? And now I'd like to talk about the actual systems. The next few slides are going to be about the actual hardware that we use. To the right, what you will see is a picture of a SciEx triple TOF 5600. We also have a SciEx triple TOF 6600. The 6600 is used for small molecule MetID. The 5600 is really dedicated to oligonucleotide studies. And for these both of these instruments, we do electrospray ionization. We either use positive or negative ionization, and that depends on your compound and the metabolite. So some compounds will go negative, some will go positive, and sometimes you will have metabolites that are the opposite. The mass accuracy of these instruments is plus or minus 5 ppm, and the accuracy is not just on the intact component, but it's also on the fragments, which helps with our structural elucidation. And now I'd like to talk about the radio detection systems. The inline radio flow detector that we use is called a beta RAM, and it's made by LabLogic. And the example radiochромatogram that you see to your right is one of the radiochromatograms from that system. We also do the radio-quantitation samples, but those are fraction collected, and they're detected by what's called a top count NXT. It's a static detector, and it has increased accuracy and sensitivity compared to the radio flow detectors. However, it is much more time consuming analytically. The integrated peaks on the radiochromatograms, as you can see on the example, you have an M1, M2, M3, and M4. Those are all metabolites and the parent. And hopefully this is what your plasma samples look like. So you have mostly parent and you have a few integratable metabolites. And what we use the integration for is to decide the percent of radioactivity for each component in the separate matrices. The method development that we do for these, we try to do this as much as possible on the radio detector, the radio flow through detector, because that's faster than trying to do that on the top count. And the target is to get sufficient separation between the peaks to determine percent of radioactivity attributable to each component. The analytical runs are practically always greater than 20 minutes. Our normal range is 20 to 60 minutes, and it depends on the complexity of the samples. The recovery of the radioactivity from the column is also determined. So, and that's determined in duplicate, and a recovery is of greater than 90% is also required. So when we do that, we do 2 injections without the column and collect that, and 2 injections on the column and collect those samples, and those samples are compared on a liquid scintillation counter. The electrospray ionization that we use for the method, the final method is shown to the sponsor with the radiochромatogram so they can see what our separation looks like, and it's agreed to by the sponsor. The fraction collection, if we need to do that for profiling for urine and fecal samples, we will do that. If we need to do method development with the top count, that extends your timeline significantly. For metabolic profiling and identification, our target is to get any metabolite that's 5% or greater of the radioactivity in each matrix. And the reality is, if we identify a metabolite and it's less than 5%, we will still report it. And what we look for are the expected metabolic pathways, and if you have any previously reported metabolites, we will look for those as well. And then we do targeted MS-MS, we interpret the product ion spectra, we propose metabolites with structures, and then you also get a proposed metabolic pathway. So that shows the path that your parent goes from one metabolite possibly to a second metabolite, and I will show you something like that in the next slide. And if you have any authentic reference standards for metabolites, we will use those for definitive determination. We use SciX software and SciX hardware. So we also have Metabolite Pilot and PeakView. They are also used to aid the search for unknown metabolites. And some of the things that they can do for us is they can do some predictive fragmentation. They can also do isotope pattern filtering. We can also look for precursor ion and neutral loss filtering. And the accurate mass, as I mentioned before, is used to confirm the molecular composition, and it's also used to confirm the proposed structure because of the way that we get accurate mass on the fragments as well as the intact parent. So now I'd like to talk about metabolite profiling and identification. The 2 structures that you see at the bottom, one is verapamil with the fragmentation that we would see in a mass spec, and the other is the metabolic scheme of verapamil. And the reason I've shown these is that what I want to demonstrate is that the fragmentation of the individual components with comparison to the parent fragmentation aids in the structural elucidation. So the verapamil compound fragments in a number of ways that give us one fragment to the right and 3 fragments to the left, which actually help in structural elucidation. And for verapamil, as you can see on the right-hand side, there are a number of metabolic pathways that this compound takes. It does N-demethylation, O-demethylation, N-dealkylation, and combinations thereof. And the accurate mass that we get for the fragments, as demonstrated on the structure on the left of the M/Z of 260.165, that helps in our structural elucidation of the metabolites. But what you should know is that while we have very good hardware and we have very good software, really the heart of the biotransformation group is the experience of the actual scientists themselves. We have 4 PhD level scientists, and average is 16+ years of experience in either biotransformation or at least in pharmaceutical sciences. And we've been doing, QPS itself has been doing 10 to 12 regulatory studies per year since 2002. The radio-quantitation samples are done, as I said, those are done after the profiling, and those are quantitatively profiled. Each radioactive peak is identified, integrated, and compared to the amount of radioactivity in that matrix. The urine and fecal samples are reported as the % of total dose administered to the subject, and depending on the amount of radioactivity, we will either use the radio flow detector or an HPLC fraction collector with the top count. Plasma is always done on the top count, and the concentration of each radioactive component observed in plasma is reported as nanogram or possibly microgram equivalents per mil, and those are always done on the top count. The individual components are analyzed using Win-non-Lin, and what you get back in your report is total area under the curve for all the components and with a % AUC for each component. The % AUC for each component is actually very crucial because this gives you your systemic exposure of the various components. In addition, you will see the AUC pooled plasma samples that are analyzed for each subject. The reported data, you will see 2 tables to your right. Those are typical of the data that you will get in a report. The table on the top shows the radio-quantitation in urine, and the metabolites are listed on the left-hand column going down with the parent at the bottom and the time points going across, so you can see as the metabolites are rising or falling, and the cumulative amount of % dose excreted in urine by component is listed at the bottom. And the route of excretion, one of the things that you want to look at for that particular thing is the clearance of unchanged parent versus metabolites. And for the plasma at the bottom, what you'll see is the same metabolites as were shown in the urine, the same metabolites, but the time points are slightly different because of the way that the collections were done, and then the AUC is listed to your right. The % AUC at the right, the far right column, that's the important column for these. So as you can see, M2 and M3 both are greater than 10% of the drug-related material. So that's crucial to know for studies going forward. So you will need to know whether the preclinical samples have sufficient coverage of those pathways. And the report that you get is suitable for regulatory filing and has all the proposed metabolites with the fragmentation that we showed, and it has the structural elucidation. The parent metabolites reported as % of dose in urine and feces, and the parent metabolites are reported as microgram or nanogram equivalents per gram or mil in plasma and as % of AUC. And the key takeaways from this study are the excretion pathways of parent metabolites may provide information on future clinical studies. So you may need to worry about drug-drug interactions. Do you have renally impaired subjects that you may be worried about? Circulating metabolites, do you have 10% or greater of the drug-related material of any metabolite? And can you compare this to the preclinical ADME studies? And what you really need to know is, are there any human-specific metabolites? And if so, how large are they? And you may need to worry about further tox studies. The regulatory ready report includes proposed metabolites with structural elucidation and metabolic pathway, the excreted parent and metabolites as % of total dose administered, circulating parent and metabolite as % of AUC, which is also known as systemic exposure, and then the comparison of the AUCs across subjects, which may or may not identify potential inter-subject variability. And with that, I'd like to thank you for your attention, and we appreciate your time today. And for more information, please visit qps.com. Thank you.